Okay, hi everyone. Today I'm going to go through with you, or today I'm going to teach you how to compare basicity of phenylamine, pyridine, and ammonia. All right. Okay, so let's start with ammonia. Okay, so in order to compare the basicity for all these nitrogen compounds, we actually have to look at the availability of the lone pair on the nitrogen. All right. So let's start from ammonia. So you look at methane, right? Methane, I hope everybody knows, is sp3 hybridized. So the carbon actually has 4 regions of electron density, and all of them are sp3 hybridized, which means it's like that: 1, 2, 3, 4. Okay, all of them are actually sp3 hybrid orbital. Right, all of them are sp3. Okay, right, sp3, sp3. All right, so there are 4 regions of electron density. The shape is tetrahedral. All right, so if you look at ammonia, the nitrogen also has 4 regions of electron density, right? 4 regions of electron density, as you can see: 1, 2, 3, 4. 3 bond pair and 1 lone pair. So in fact, this nitrogen, it actually is sp3 hybridized, right? It's sp3 hybridized also. All right, so let me draw it up. So it actually looks like that, right? sp3 hybrid. So you expect to see 4 sp3 hybrid orbitals, just like methane. It's just that this lone pair on nitrogen is in the is in the sp3 hybrid orbital. Can you see that? Yeah. All right. So if I have to put in all the hydrogen, they are spherical in shape. So this is what it looks like. And what I'm drawing is actually the structure of ammonia, all right, which is a trigonal pyramidal. Yeah. Okay, so I'm going to look at phenylamine. If you look at phenylamine, this nitrogen here, all right, actually has 3 bond pairs and 1 lone pair. Right, so typically it should also be sp3 hybridized, right? sp3 hybridized. So this is already drawn quite nicely, phenylamine. So you can see that the lone pair on nitrogen can actually delocalize into the benzene ring. That's what they're trying to show, right? It can actually delocalize into the benzene ring. All right, okay, but actually the truth is this: because usually there's delocalization, this nitrogen is kind of smart, right? It actually can convert itself to a sp2 hybrid orbital. So once it converts itself to a sp2 hybrid orbital, or undergo sp2 hybridization, it will actually end up with a trigonal planar shape. All right, so you can look at the nitrogen here. In fact, it's trigonal planar. All right, and the lone pair will end up being in the p orbital. This is the p orbital, and the lone pair can again delocalize into the benzene ring. In fact, if the lone pair is in a p orbital, all right, which means it's actually parallel with all the p orbitals of the benzene ring, correct? It's parallel with all the p orbitals of the benzene ring, so it's actually easier to delocalize. It's definitely easier to delocalize in. So actually, there are some different books will say different things. Some books will say actually for nitrogen in phenylamine is sp3 hybridized, and some actually is sp2 hybridized. But actually, I would say that it could actually exist as sp3 or sp2. In fact, sp2 is what we call the transition state. Okay, but I won't go in detail. All right, so but it always depends on your school, because some schools will expect students to say is the nitrogen in phenylamine is sp2 hybridized. Some schools will say is actually you have to write sp3 hybridized. All right, so check with your school. All right. Another thing I want to point out is this. So how do you know when a lone pair can delocalize, right? How do you know when a lone pair N can delocalize? This is the idea, right? This is the concept. Look out for the nitrogen of the lone pair, right? It must be attached to an atom with a double bond. Okay, so this is like your benzene ring, right? So if the nitrogen is attached to an atom with a double bond, generally it will be able to delocalize. Okay, generally it will be able to delocalize. So again, look out for nitrogen attached to an atom with a double bond. Okay, so then it can delocalize. Okay, let's look at phenylamine. All right, so okay, maybe I'll say this. So normally you can delocalize. We say the lone pair is actually less available, right? Okay, we will always say less available, right, to for donation or to accept a proton. All right. Okay, let's look at phenylamine. Okay, let's look at not phenylamine. Let's look at pyridine. Okay, this is what pyridine looks like. Can you see? This pyridine, actually, if we look at it carefully, there's a double bond to the end. Right, there's a double bond to the end. So, and there's a lone pair on the end. There's actually a lone pair on this end here. You see that? There's a lone pair on this end. So the thing is this. So a lot of students think that the lone pair can delocalize. All right, they can delocalize. But let's study a little bit in detail. All right. So look at ethene. All right, ethene. The carbon here has a double bond and it's actually sp2 hybridized. The nitrogen here, which is also has a double bond, and this nitrogen I want you to know is also sp2 hybridized. All right, it's actually sp2 hybridized. Okay, so can the lone pair delocalize then? Right, can the lone pair delocalize into the pi bond? Right. So if you look at carbon, okay, if you look at carbon over here, all right. So carbon, actually think about it. Let me draw it out. Okay, there's actually a sp2 hybrid orbital. This is a sp2 hybrid orbital, and this is a sp2 hybrid orbital. So it looks like that. If a carbon with a double bond, just to show you again. All right. So in fact, I'll normally think of it. This is sp2, sp2, and sp2. So this is actually trigonal planar. All right. So don't forget, there's actually a pi bond here. All right, a p orbital here, and this p orbital has a electron. Right. So the other p orbital on carbon also has electron. That's where you form the pi bond. Can you see that? So if I try to draw nitrogen with the one with the double bond, right? Nitrogen with a double bond. So let me try to draw it again. So if I look at nitrogen, okay, let me use a different color. Okay, nitrogen with a double bond, right? So it looks like that. So can you imagine, all right? So I hope you imagine this N is also sp2 hybridized. So it's sp2 hybrid orbital, sp2 hybrid orbital, and sp2 hybrid orbital. All right, and all are trigonal planar. All right. So where's the lone pair? Actually, this is the lone pair. The lone pair is over here. And actually, there's a p orbital on nitrogen also, and there's there's actually a p orbital on nitrogen. So the electron here will actually form a pi bond. That's why you get a pi bond, right? So nitrogen with a double bond, there's a sigma and a pi bond, right? Sigma and pi bond. So the lone electron here will form a pi bond. Yeah. So but what's more important for you to realize is, where is the lone pair? Okay, the lone pair is actually in a sp2 hybrid orbital. So look at this picture here. Maybe it's a bit clearer, right? If I draw it one more time. All right. So let's see. So this nitrogen here, sp2 hybrid orbital, sp2 hybrid orbital, and this sp2 hybrid orbital. All right. And this lone pair in the sp2 hybrid orbital is perpendicular to the pi bond. All right, perpendicular to the pi bond. So what I'm trying to show you is this. All right, so this is the pi bond. You can see that's the pi bond. All right, this is a pi bond, and this lone pair is in a sp2 hybrid orbital, and it's perpendicular. So because it's perpendicular, all right, 90 degrees, I want you to know that this lone pair cannot delocalize. Right, cannot delocalize. Okay, same goes for this one. This one also cannot delocalize. There's nothing to delocalize anyway. Cannot delocalize. There's nothing to delocalize into. Okay, so what's more important is this. If you see pyridine, you see the lone pair. Understand that the lone pair is in the sp2 hybrid orbital and it cannot delocalize. Okay, and cannot delocalize, which means, so what does it mean? So it seems that since the lone pair in phenylamine can delocalize, phenylamine must be the least basic. Okay, because the lone pair will be less available and to accept a proton, so it's going to be least basic. Okay, so the tricky question comes in when we have to compare ammonia and pyridine, because both the lone pair cannot delocalize, right? So we're going to learn this little concept here. All right, so let's run through this part here. Okay, let's run through this. Okay, I'm going to show you what happens when nitrogen undergo sp3 hybridization. Okay, nitrogen, you can see it has 7 electrons, right? So it's always 1s2, 2s2, 2p3. Right, so that's what I'm drawing, 2s2, 2p3. So when I say it undergoes sp3 hybridization, what it means, it takes one s, this is actually s1p3, yeah? It takes one s orbital and 3p orbital. So all of them will combine, everything here, okay, all of them will combine to form 4. Okay, remember, 4 equal sp3 hybrid orbital. So they all look like this. Okay, They all look like this, and that's why when we try to draw it out, these orbitals wants to be arranged as far apart as possible based on the VSEPR theory, right? So they want to be arranged as far as possible, so the shape will be this way, tetrahedral first. All right, tetrahedral first. All right, but one of them will be the lone pair. Can you see that? All right, so it's something like this. Okay, so you can see that this one is actually in a sp3 hybrid orbital. That's what I'm trying to run through with you. Okay, so sometimes you're going to ask this question, sp3 hybrid orbital, right? sp3 hybrid orbital, how many percent s character? We'll say how many percent s character. So you can see that we use 1s and 3p. All right, 1s and 3p. So the percent of s character, right, is equals to 1 out of 4. So 1s and 3p. So 3 plus 1 is 4. So it's 1/4. Okay. So we use, it has what we call 25% S character. Okay, percent S character. You're gonna understand this S character concept later, but I just want to calculate like how many percent of S in an sp3 hybrid orbital. Okay, let's look at the next part. Okay, if it's sp2 hybridized, right, what it means is this. You take 1s and 2p orbital. See, what I'm circling, I take 1s and 2p orbital, right? So end up becoming a 3. There will be 3 equal sp2 hybrid orbital. Yeah, so this one is still unhybridized. This is just a p orbital that hasn't been touched, right? So the p orbital here, it hasn't been touched. So if I try to draw nitrogen, which is sp2 hybridized, this sp2 hybrid orbital, right, how will they be arranged? Right, how will they be arranged? This is how they're going to be arranged. Trigonal planar, right? 1, 2, 3. All right, and you notice there's 1 electron here, 1 electron here, and 2 electrons here. Can you see that? So there's 1 p orbital that hasn't been used, so I'm going to use a different color. It's actually over here. All right, and this is a 1 electron that hasn't been used. Okay, what am I drawing? I'm actually drawing the shape of this nitrogen. All right, so you notice, all right, if you notice, I just drew this lone pair in an sp2 hybrid orbital. All right, and it's perpendicular. So the pi bond, where's the pi bond? The pi bond is this one here. Okay, form with another p orbital. Yeah, so that's the pi bond. Can you see that? So I want you to know that you can see now that this one actually is not delocalized, right? It's actually not delocalized. Right? Okay, so but what's more important now, you're going to learn this. I'm going to ask you how many percent S character. So what's the percent of S character in this one? So that's you're using 1S and 2P. All right, 1S and 2P. So percent S character for sp2, right, is, you can see, it's actually 1 out of 3 times 100%. So it's approximately 33%. Okay, approximately 33%. So this is a very important concept now, so pay attention. So you must know that S orbital is actually closer to nucleus, right? Because if you draw the energy line, all right, we draw something like this. Okay, maybe I just draw it here. So we always say 2s, this energy, then 2p. So we know that 2s is actually closer to nucleus, and 2p actually is further away from nucleus. So the one we have more S character, right? 33% compared to 25%. So one has more S character, this one has more. So sp2, sp2 more S character. Okay, so what does it mean? It means the sp2 orbital, right? Orbital is closer to the nucleus. So this is a very important concept. All right, so S orbital is of lower energy and closer to, so let's look at answer key here. So S orbital is of a lower energy and closer nucleus compared to the P. So sp2 has 33% S, sp3 has 25% S character. So this is very important now, take note. Hence sp2 hybrid orbital will be, sorry, it's here. sp2 hybrid orbital will be closer and more strongly attracted to the nucleus. Why is that so? Because it has more S character. Okay, because it has more s character. So sp2 hybrid orbital will be closer and more strongly attracted nucleus. So what it means is this, all right? What it means is this. It means that the electrons in the sp2 hybrid orbital are less available for donation. So because it's closer to the nucleus, it will be less available to donate, and it's also less available to accept a proton. Hence, it's actually less basic. Okay, so it's end up being less basic. All right. Okay, so let's look at now let's look at the whole thing as in comparison with everything here. All right. So what it really means is I'm going to just draw it out over here. So the way you look at it, right? For phenylamine, the lone pair here can delocalize. Okay. The lone pair. Just say the lone pair can delocalize, right? Into the pi electron cloud of the benzene ring. Okay, so can delocalize. So imply what I say is less available. All right, so this one is least basic. Can I say that? It's least basic. Okay, so how you compare the basicity of pyridine and ammonia? So pyridine, I will say this one is actually sp2 hybrid orbital. So we say this lone pair is an sp2 hybrid orbital. It's actually closer to nucleus. Why? Because it has more s character. More s character, right? So closer to the nucleus, which means it's gonna be less available for donation. It'll be actually less basic. Okay, so compared to what? Compared to ammonia. So ammonia, the lone pair, we look at the lone pair here. This lone pair is in the sp3 hybrid orbital. sp3, right? So actually it has less s character because only 25%. Less s character imply it is actually more available for donation. So out of all of them, you'll notice that ammonia is the most basic compared to pyridine, compared to phenylamine. All right, so that's how we look at it. Okay, I'm going to just go through one question to see whether you can apply this question in a certain question here. All right. Okay, so let's try this question. Okay, let's look at this amino acid histamine. Okay, they say state the hybridization of the nitrogen labeled A. Right, so this is like just now pyridine, remember the N with a double bond. So I guess this N, so we just learned it, right? This N has a double bond, right, in a single, so it looks like pyridine. So the hybridization of this nitrogen must be sp2. Okay, I hope you realize it must be sp2. Then they say explain why is it less basic than the nitrogen labeled B. So this nitrogen B, it looks like that. Okay, so it looks like this. So you notice this lone pair now is actually in a sp3 hybrid orbital. All right, so I guess we just went through this, so I believe you know that this one is 33% s, right? 1 out of 3, right? 33% s, and this lone pair is actually 25% s, right? 25% s. Okay, so 1 out of 4, right? So the one that is more s character, the lone pair is closer to the nucleus and it's less available, it is less basic. Okay, so this is the reason. Okay, so let's look at answer. More s character, lone pair more strongly attracted by the nucleus. For this one, the lone pair here is more strongly attracted by the nucleus than the lone pair in the sp3 hybridized N, so less available for protonation or less available to accept a proton. Okay, less available to accept a proton. All right, okay, let's look at the next one. Okay, we have less available to, maybe I put for, maybe I just say for donation, it's better, right? For donation, or less available to accept a proton. Okay, maybe that's a bit clearer. Okay, let's move on. Next question. Explain why the nitrogen labeled C is less basic than the nitrogen in A. So if you look at these two nitrogen, all right, these two nitrogen here. So again, I'll say this, right? I'm just going to draw it out here. Okay, so I mentioned that this lone pair here, because it's in a sp2, so I mentioned that it cannot what? Cannot delocalize. It cannot delocalize, right? Okay, if you look at this nitrogen, there's a lone pair here, and what I mentioned to you just now was this: if the nitrogen is attached to an atom with a double bond, right? So it's something very close to phenylamine, right? It's attached to a See if here, so it's double bond, right? Okay, this nitrogen is attached to a atom with a double bond. So this, because it's attached to an atom with a double bond, it can actually delocalize, all right, into both the pi electron cloud of the CC and CN double bond, right? It can actually delocalize. So if it can delocalize, if this one can delocalize, I put can delocalize, it means imply it must be less available. Less available imply it is going to be less basic. All right, so the nitrogen labeled C is actually less basic compared to A. So let's see how you answer. The lone pair on N is found in the sp2 hybrid orbital, which is planar with the benzene aromatic ring, yeah, not benzene, but with the ring. Okay, so it is not, okay, the word you take note, you have to write this, is actually not delocalized, right? It's not delocalized into the ring. Okay, it's not delocalized into this ring. However, the lone pair on N labeled C, which is this one here, is delocalized into the pi electron cloud, hence less available to accept a proton. Alright, so I hope this clarifies some more tricky basicity questions regarding nitrogen compounds. Alright, so please take note. Right, it may just come up for your prelim questions.